Hello Year 12, or should I say Year 13, and welcome to this second lesson on the topic of entropy. Today we're going to be looking at something rather grand, the entropy of the universe. But first, let's remind ourselves what we did last lesson. We saw that some reactions that were endothermic occurred spontaneously. And therefore it isn't just enthalpy that controls whether a reaction will go without needing extra energy. Some endothermic reactions will proceed without constant energy being supplied. We looked at entropy and we saw that it is a measure of disorder of a system, and that the natural change is from a system to increase in entropy. There's a positive entropy change. And we started to look at some reactions to see if we could judge whether or not entropy was increasing or decreasing. And that was your homework. So today we'll be finishing off that idea and having a look at those reactions that you looked at for homework, or for the first part of your homework, to see if we can see any general trends in whether a reaction is spontaneous or not. We will then go on to calculate the entropy change of the system, to actually put a number on it. And we will also do the same thing for the surroundings. And once we know the entropy change of the system and the surroundings, we can calculate the total entropy change, that is, the entropy change of the universe. And this is the key idea, because it is this that determines whether a chemical reaction will go or not. Will a chemical reaction move from reactants to products? If so, how far? That comes from the entropy change of the universe. But let's remind ourselves, entropy measures the amount of disorder. A system that is very disordered, like for example this P and this Y here, that has a high degree of disorder and high entropy. In contrast, a system that is far more ordered, far less disordered, like this E over here, this has low entropy. We saw that in a spontaneous process, the direction of change is always from a more ordered, less probable system to a more disordered, more probable system. This always happens. If you took a tube of Smarties where one end was full of green Smarties and the other end was full of red Smarties, and you shook them, you'd always end up with the Smarties being mixed. And the reason for this is just to do with probability. Disordered states are far more likely to exist or emerge than ordered states. There's just so many more ways you can have a disordered state than an ordered state. You will always see a disordered state. And to put some actual numbers on it, if we go up here and we look at water, well, the particles here, they are able to vibrate a little bit, but actually they're in a fixed position. They can't rotate, they can't move. They don't have that many ways of ordering themselves. There's not that many ways to order the energy within those particles, and so solid water has a rather low entropy. Notice the units joules per mole per Kelvin. Do not confuse the units of entropy with the units of enthalpy. In particular, entropy is always joules per mole per Kelvin. Enthalpy is kilojoules per mole. In water, these particles are able to move slowly, they're able to translate, they're still able to vibrate, and they're able to rotate. So that means there's a lot more ways of arranging the energy within these particles, lots of different options available to them, and consequently liquid water has a much higher entropy than solid water. By the time we get to a gas, well, these are completely free to move, rotate, vibrate as they see fit. A huge degree of options available to them, and therefore there's a substantial increase in entropy going from liquid water to gaseous water. Just to remind you, all of these values are at 298 Kelvin. That means they've all got the same amount of energy available to them. It's just there's not that many ways to order the energy in the solid, far more ways to order the energy in the liquid, and a huge number of ways to order that energy in the gas. In summary, the entropy of a gas is much, much larger than the entropy of a liquid, which is bigger than the entropy of a solid. If you heat up a solid, liquid or gas without changing state, there is more energy to share, and therefore there are more options available for vibration, rotation and translation. There's more disorder and higher entropy. So heating up something even without a state change leads to more entropy, as there's more energy and more ways to share that energy. Finally, if you have more of a chemical, there are more ways of arranging the particles, and so higher entropy. So 2 moles of nitrogen gas has twice as much entropy as 1 mole of nitrogen gas. And we looked at some specific examples here: bromine liquid becoming bromine gas, liquid to gas, an increase in entropy. Solid and a gas becoming a solid, that is a decrease in entropy, we're losing a gas. Free ions becoming a solid, they're losing entropy, that's far more ordered. 2 gas molecules becoming 2 gas molecules, well, not much of a difference there. They're all about the same size. There's not much of a change in entropy there. 3 gas molecules becoming 1 gas molecule and 2 liquids, that's clearly a decrease in entropy. And a free moving ion and a fixed solid atom becoming a fixed solid atom and a free moving ion, again, that's fairly similar on both sides in terms of entropy. For your homework, you hopefully looked at these 7 reactions. Here we took ammonium nitrate and we dissolved it to create free moving ions, and we saw a decrease in temperature. Well, the reaction is clearly endothermic, delta H is positive. Because the system went from a solid to free moving ions, clearly the entropy change of the system, the chemicals in the reaction, that increased. They've got more entropy at the end than they had at the start. However, because it was endothermic and this got cold, it sucked in energy from the surroundings, which got colder. That means the surroundings have less energy available to them, and so they're more ordered. The entropy change of the surroundings is negative. The reaction was spontaneous. It went by itself without needing a constant energy input. It got cold by itself. Second example was hydrochloric acid and magnesium ribbon. And this was a spontaneous reaction that generated magnesium chloride and hydrogen. We created a gas. Therefore, the entropy change of the system is very positive. The reaction was clearly exothermic. It gets quite hot, delta H minus, meaning the surroundings got hotter as energy was released into the surroundings. Because the surroundings had more energy, there's more options available for how to arrange that energy, so they become more disordered, positive delta S surroundings, and the reaction was spontaneous. For the combustion of hydrogen, hydrogen gas, 2 of those, reacted with an oxygen gas molecule to form 2 water molecules. Clearly a decrease in entropy of the system, but the reaction was very exothermic. The surroundings got hotter, so therefore they increased in entropy. And once ignited, the reaction was spontaneous. It only took a small spark, and then the rest of the reaction just proceeded with no further energy input. Here, acid and carbonate. We added glacial acetic acid to ammonium carbonate. That gave off carbon dioxide. Clearly, creating a gas from a solid and a liquid means we've got an increase in entropy of the chemicals themselves of the system. But, as we can see from the thermometer, the reaction was endothermic, delta H positive. So the surroundings got colder as they gave up energy to the system, or to the test tube. Because the surroundings lost energy, they became more ordered. Entropy change of the surroundings is negative. The reaction was, however, spontaneous. This is a very unusual reaction between two solids, where we take barium hydroxide, solid, and we mix that with ammonium chloride, solid, and that generates two lots of water. We've generated a liquid, plus barium chloride, which is free moving ions dissolved in that liquid, and two lots of ammonia gas. So two solids developing a liquid, a solution and a gas, well, clearly the entropy change of the system is positive. But as you can see, the temperature dropped massively. It's an endothermic reaction. The surroundings got colder as they released energy into this beaker. They therefore became more ordered. But yet again, despite this, the reaction was spontaneous. You mix those solids together and it goes without needing any energy input. A redox reaction here between sodium nitrite and ammonium chloride. And this actually releases nitrogen gas. So we can see that the gas being produced means the entropy change of the system of the chemicals themselves is positive. Difficult to see, difficult to know here, but the reaction is actually exothermic. You wouldn't really know this. You'd have had to have researched that, and I wasn't expecting you to, but actually delta H is negative, meaning that the surroundings got hotter and the surroundings went up in entropy. It clearly says on the video, once started, the reaction proceeded with no further energy input, so the reaction was spontaneous. Contrast that with this reaction, the thermal decomposition of zinc carbonate, where we generate carbon dioxide from a solid, the system clearly therefore going up in entropy. But as you hopefully know, thermal decompositions are endothermic. That means the surroundings have actually got colder. So as this reaction proceeded, they took in energy was needed. So energy was needed to make this happen. So the surroundings have become more ordered, delta S negative, and the reaction was not spontaneous. I've summed all of that together in this table along with a couple of other reactions that I want to discuss. First, let me just point out that the enthalpy of the system and the entropy of the surroundings are always opposite directions. So if we have an endothermic reaction, the surroundings lose entropy. If we have an exothermic reaction, the surroundings gain entropy. So I'm going to blank out this column because it's covered by the entropy change of the surroundings. Let's focus on the first few. In this case, for the dissolving, there was an increase in entropy of the system, but a decrease in the surroundings, and it was spontaneous. The same is true for that solid-solid reaction and the acid and the carbonate, but look here. For the fourth reaction, the thermal decomposition, we also have an increase in entropy of the system and a decrease in entropy of the surroundings, but this reaction is not spontaneous. So we don't know whether these are going to be spontaneous or not. For the magnesium and hydrochloric acid and the redox reaction, both the entropy of the system and the entropy of the surroundings increased, and these were both spontaneous. And in fact, it is generally, well, it is true, it's always true, that if the system increases in entropy and the surroundings increase in entropy, these are always spontaneous. They may go very slowly, they may need help to go by activation energy or an ignition source, but they are always spontaneous. For hydrogen and oxygen, we lost entropy of the system, but we gained entropy of the surroundings, and that was spontaneous. But contrast that with the Haber process. From GCSE, you know that the Haber process loses entropy of the system, and we saw that last lesson as well, but it is exothermic, which means the entropy of the surroundings goes up. So again, we're not sure whether a decrease in entropy of the system and an increase in entropy of the surroundings is going to be spontaneous or not. For photosynthesis, however, where we've got 6CO2 gas plus 6H2O liquid going to C6H12O6 solid plus 6O2 gas. There's clearly a decrease in entropy of the system. It's also endothermic, and this reaction is not spontaneous. And in fact, any reaction where both the system and surroundings lose entropy is never spontaneous. So in two cases, plus plus and minus minus, we actually know whether a reaction will be spontaneous or not. But if the system and the surroundings have different signs, it's a bit more complicated, and this is where we have to put numbers on it. So the rest of this lesson, we are going to be calculating entropy changes of the system, of the surroundings, and then of the universe. In the old spec, the 2008 A-level spec, the data book was huge. It had pages and pages of data. And I just want you to focus here that next to all of these molecules, there is an enthalpy of combustion, an enthalpy of formation, and an entropy value. And just like standard enthalpies of combustion and enthalpies of formation, standard entropy values can be determined experimentally and tabulated. And this allows us to calculate an entropy change of a reaction just as we would an enthalpy change. Entropy change cycles are just like formation cycles. So let's say we're interested in the enthalpy change of this reaction, sulfur dioxide and hydrogen sulfide forming sulfur and water. Well, going from reactants to products is the same as going against this arrow and with this arrow. This should be familiar to you from your topic 8. So the enthalpy change of the reactions is enthalpy of formation of the products minus enthalpy of formation of the reactants. And we are making both of our products and reactants, in this case, from a toolbox of elements. And you've done loads of cycles like this. Well, an entropy cycle is just the same. If we want to calculate the change in entropy of this reaction, we can use standard enthalpies. Now, remember, everything has zero enthalpy at absolute zero. And as we warm a chemical up, we can see how much energy it's absorbing as it warms, and therefore it is possible to calculate entropy changes as everything is warmed from absolute zero. As with the formation cycle, if we want to go from reactants to products, we go against the entropy of the reactants and with the entropy of the products, and just like before, entropy of the products minus entropy of the reactants. That's how you do it. So let's put some numbers in this, and we'll start with enthalpy H. Right, how would we calculate the enthalpy change of this reaction? Well, it's products minus reactants. So product, silicon is 0, magnesium oxide is minus 601.6. There's 2 lots of carbon monoxide, which is minus 110.5. And there's 4 lots of hydrogen, which is 0 because it's an element. And from that we would subtract the enthalpy of formation of the products. Sorry, the reactant. So magnesium silicate minus 1549 plus 2 times, and methane is minus 74.87. That's 4 times 0. So let's work that out. Plus 876.14 kilojoules per mole. So let's do the same thing with entropy. So what is the entropy change of the reaction? Well, the entropy change is again products minus reactants. So the product, silicon, 18.81 plus magnesium oxide, 26.95 plus 2 times 197.7 plus 4 times 130.7 minus the entropy of the reactants. So that would be 67.76 plus 2 times 188.7. Notice from these numbers the gases have much higher entropies than the solids in the table, and that is to be expected. Also notice that they are all positive numbers. Entropies themselves are always positive numbers, and that means you're less likely, though it's not impossible, but you're less likely to make a mistake when calculating an entropy change. So let's do this. 5 plus 518.8 joules per Kelvin per mole. Notice joules per Kelvin per mole there. Is this to be expected? Would we expect a positive entropy change? Well, yes, we would. We're going from 2 gas molecules to 1, 2, 3, 4, 5, 6 gas molecules. And therefore that would be a big increase in entropy as expected. So over to you. Calculate the entropy change for the hydrogenation of ethene and calculate the entropy change for the Haber process. Have a go, pause the video, then restart. Okay, entropy change of the reaction. Entropy of the product, that is ethane, which is plus 230. Minus entropy of the reactants, which is ethene plus 220, plus hydrogen 131. So that gives you an answer of minus 121 joules per Kelvin per mole. And for the Haber process, the only added difficulty here, as you've got to remember, it's 2 lots of ammonia, so 2 times plus 193 minus the reactants, so that is 1 nitrogen plus 191 plus 3 lots of hydrogen, and working that out is minus 198 joules per Kelvin per mole. Would we expect both of those to be negative? Well, yes, we would. We've got 2 gas molecules becoming 1 gas molecule, negative entropy change, and we've got 4 molecules of gas becoming 2 molecules of gas, negative entropy change. That is as expected. So, just to remind you, in a spontaneous process, the direction of a change is from a more ordered, less probable state to a more disordered, more probable state. This always happens. So let's consider the oxidation of magnesium. Magnesium and oxygen forming magnesium oxide. Well, clearly here we are ending up with a more ordered state. But yet this is clearly a spontaneous reaction. So how do those two things go together? Well, let's just convince ourselves that there is actually a decrease in entropy. Putting in the numbers there, we can see that the entropy change of the system is clearly negative, minus 216.6 joules per mole per Kelvin, and the entropy of the system decreases. Yet this reaction is clearly spontaneous. So what's going on? Well, first we've got to consider where the energy goes, and this is where I tried to guide you on the homework. The reaction of magnesium and oxygen to form magnesium oxide is clearly exothermic. Where does all of the energy go? Well, it goes into the surroundings. Energy is transferred to the surroundings. Because the surroundings have more energy, this means there are more vibration, rotation and translation options available, and so the surroundings become more disordered. They gain entropy. Can we calculate this? Well, yeah, it turns out there's a really simple equation to calculate the entropy of the surroundings. And it is this. To calculate the entropy change of the surroundings, it is the minus enthalpy change over the temperature in Kelvin. Why is it minus? Well, the reason it's minus is if you've got a chemical reaction that is losing energy, that energy is going out of the system and it's going into the surroundings. The system's losing energy as the surroundings gain energy. So obviously it's the negative sign of what's happening to the system. Just like when you did your experiments in topic 8, you used minus Q over N. You calculated the change in energy of your calorimeter and your system, and your surroundings. You calculated the change in energy of the water, and you said, well, the energy change of the system must be the opposite sign of that. So minus delta H, because if energy has gone out of the system, it's gone into the surroundings. And if it's gone into the system, it's gone out of the surroundings. And we divide that by the temperature at which this energy is being transferred. So here's the enthalpy of formation of magnesium oxide. Clearly, because these are both elements, their enthalpy of formation is 0. And so therefore the enthalpy change of the reaction is minus 1203.4 kilojoules per mole. So plugging that into the equation, the entropy change of the surroundings is minus the enthalpy change of the reaction over T, which is minus 1203.4 times by 1,000. Why? Because as I've said, entropy is always measured in joules per mole per Kelvin, whereas enthalpy tends to be given in kilojoules per mole. So we must times that by 1,000. Divide by temperature minus, so the enthalpy change, the entropy change of the surroundings is plus 4,038 joules per mole per Kelvin. In other words, the entropy of the surroundings increases. Let's do the same thing for this reaction. Well, we saw previously that delta RH for this reaction was plus 876.14 kilojoules per mole. So it's an endothermic reaction. So delta S of the surroundings is minus plus 876.14 times by 1,000 to put that in joules, divided by the temperature at which this is occurring, let's say 298 Kelvin. So 876.14 times by 1000 divided by 298 is minus 2940 joules per Kelvin per mole. So the surroundings here have lost entropy because it is an endothermic reaction. So we now get to one of the most important ideas in science. It's called the second law of thermodynamics, and it controls a huge amount of reactions, not just chemical, but whether things will occur or not. And it says, in a spontaneous process, the entropy change of the universe always increases. So as long as the universe gets more disordered, a reaction can occur. And the universe is made up of the system and the surroundings, and we now know how to calculate the entropy change of both. If a system gains entropy and the surroundings gain entropy, then clearly the entropy change of the universe is positive, and this is always spontaneous. In contrast, if the system loses entropy and the surroundings lose entropy, then the universe will always lose entropy. And as it says down here, if the entropy change of the universe is negative, the reaction can never happen. So if both the system and the surroundings lose entropy, that reaction will not go without constant energy input. Where we have a problem is if the system and the surroundings have different signs. Because then we don't know immediately whether the entropy change of the universe is positive or negative, and we actually have to compare the size of those entropy changes. We've actually got to do the calculations. Some definitions that should be with you from GCSE, but just in case. The system is those particles involved in the chemical reaction or the physical process, the stuff in the equation. The surroundings is everything else that interacts with that system, be it the liquid in the glass beaker in which the reaction is being carried out, the air in the classroom which is giving energy or receiving energy from that reaction, or the buildings, everything else in the universe. They are the surroundings. Sometimes we are specifically talking about a closed system, and remember, a closed system is one that exchanges only energy with its surroundings. It doesn't exchange particles. So the particles can't get in or out, only the energy can. So let's go back to this example of magnesium oxidation. We have calculated the entropy change of the system from data, tabulated data. And we've seen that the system loses entropy, minus 216.6 joules per Kelvin per mole. But we've also calculated the entropy change of the surroundings at room temperature. We used minus delta H over T to do that. And we found that the change in entropy of the surroundings was plus 4038 joules per Kelvin per mole. And therefore the total entropy change of the universe is positive. So the reaction should and does go spontaneously at 298 Kelvin. Don't worry about the fact it needs some energy to start it off. Once it's going, it runs. That's the important thing. It is a spontaneous reaction. We could do the same thing here. We've calculated that delta S system was equal to plus 518.8 joules per Kelvin per mole. And we've calculated that at 298 Kelvin, delta S surroundings is equal to minus 2,940 joules per Kelvin per mole. So clearly, when we compare those two things, we can see that the entropy change of the universe is minus 2,421 joules per Kelvin per mole. So the reaction is not spontaneous at 298 Kelvin. However, those of you that have been following closely may have cottoned on to something. And that is the fact that temperature affects the entropy. So as an analogy, imagine if you sneeze in a busy street. Well, no one's going to notice you. It's going to make very little difference given the level of noise that already exists. No one's going to pay attention. Well, they might do now in the middle of the COVID crisis, but normally people wouldn't pay any attention if you sneezed in a busy street. However, if you sneeze in a library, that same sneeze will gain a lot of attention because it makes a big effect. If there's hardly any noise, that sneeze really will reverberate and everyone will pay attention. In a similar way, adding 1 joule of heat energy to a hot object makes a much smaller difference to the disorder than adding 1 joule of heat energy to a cold object. So if we add heat to a cold object, it makes more of a difference to the entropy than a hot object. And if you want to know why, we sort of looked at this last lesson when we were looking at Boltzmann's equation and this log factor, that the entropy is K times the log of the number of ways. And we saw that if we added 1 student, we increased the entropy. We added 2 students, we increased the entropy a lot, but not quite as much as adding that first student. Then adding that third student made even less of an impact, and the 4th student even less of an impact. So the more students we added to the classroom, the less the increase in entropy. And the same's true here. The more energy there is to start with, the less effect adding 1 more joule will make to the entropy of the system. So delta S of the surroundings, if you remember, is minus delta H system over the temperature, which must be measured in Kelvin. This means that enthalpy changes have a bigger effect at low temperatures. And this can change whether or not a reaction is spontaneous. Let's have a look at that. Calcium carbonate decomposing to calcium oxide and carbon dioxide. Here are the calculated changes in the entropy of the system and the enthalpy of the system. The entropy increases as expected because we're generating a gas, but it's endothermic as expected. At room temperature, 298 Kelvin, the entropy change of the surroundings minus delta H over T, don't forget this is in kilojoules per mole, 178 times 1000 over 298 minus means that the entropy change of the surroundings is minus 597 joules per mole per Kelvin. Comparing that to the entropy change of the system, the entropy change of the universe, 160.4 minus 597, gives an overall entropy change of the universe of minus 437 joules per mole per Kelvin. So the reaction is not spontaneous. It will not occur by itself. You can't make that reaction run. Doesn't happen. And that's why chalk sits around happily for thousands, if not millions of years at room temperature. However, if I now use 2 Bunsen's and increase the temperature of that to 1000 degrees centigrade, then I rerun the calculation. The entropy change of the surroundings, still plus 178 times 1000, now over 1273 Kelvin minus the entropy change of the surroundings is much smaller. At higher temperature, the entropy change of the surroundings is smaller. Minus 140. Now, if I work out the overall entropy change of the universe, it is a positive number, because this has suddenly become smaller than the entropy change of the system. And that means at 1000 degrees C, the reaction is spontaneous. So if I heat it to that temperature, the calcium carbonate will decompose. And as long as it doesn't drop in temperature too much, that calcium carbonate will continue to decompose. The reason we need to keep supplying that heat is obviously as it's taking in heat energy, because it's an endothermic reaction to decompose, eventually that temperature will drop to the point that the reaction is no longer spontaneous, and so we need to maintain the temperature for that reaction to occur. So some of you may be asking, well, does that mean we can actually calculate the temperature at which this reaction becomes spontaneous or not? How hot does the calcium carbonate need to be before it spontaneously decomposes? Now we know if delta S universe is negative, the reaction will not occur. If delta S universe is positive, the reaction will occur. So clearly the balance between those two is exactly when the entropy change of the universe is 0. Delta S universe is 0. The reaction flips from spontaneous to non-spontaneous when that is true. And we know that delta S universe is delta S system plus delta S surroundings. Moreover, we know delta S surroundings is minus delta H system over the temperature at which it occurs. And we can set that to 0. So since delta S universe is delta S system minus delta H over temperature, when the entropy change of the universe is 0, delta S system is delta H over the temperature. In other words, the temperature at which this flip occurs is the enthalpy change of the system divided by the entropy change of the system. Here we go. Plus 178,000 joules per mole per Kelvin, joules per mole, divided by 160.4 joules per mole per Kelvin means that this reaction will become spontaneous at 1110 Kelvin or 837 degrees C. So as long as the reaction is kept above that temperature, the calcium carbonate will spontaneously decompose to form calcium oxide and carbon dioxide. So this is your chance to put this into practice. Here are the values for the entropy change and the enthalpy change of the system. So based on those, can you calculate the entropy change of the surroundings and the universe for the reaction at 25 degrees C? Will the reaction go spontaneously at this temperature? Repeat the process for the reaction at 200 degrees C. Is the reaction spontaneous at the new temperature? At what temperature does the reaction become spontaneous? Just use my working on the previous slide to help you if you're stuck. And some more examples here. Liquid water turning to gaseous water. Here I'm giving you the entropy change, values for the entropy of water and steam. And that is the enthalpy change for the reaction. It's endothermic, as you would expect. We've got to break those bonds between the water molecules with strong hydrogen bonds in order to turn liquid water into a gas. So that is going to take in energy. Bond breaking, remember, is endothermic. I'd like you to calculate the entropy change of the system, then calculate the entropy change of the surroundings of the universe for the reaction at 25 degrees C. Is it spontaneous? At 200 degrees C, is it spontaneous? At what temperature does the reaction become spontaneous? Is that what you expected? You probably have an idea when you think that reaction will become spontaneous. If the answer isn't exactly what you expected, why not? Why didn't you get the exact answer you were expecting? Just come up with an answer, a reason for that. Now this is difficult, so pay attention. It is asked all the time. It comes up so regularly because students really struggle with it. And you've got to reason it through. Let's start easily. If delta H is positive, an endothermic reaction, that means the surroundings will lose energy and so they will be negative. If the enthalpy change is negative, then that means it's giving out energy to the surroundings, and the surroundings will have a positive entropy change. If both the system and the surroundings gain entropy, then the reaction is always feasible. You can always make it work. It might take effort, but you can always make it work. It's always spontaneous. If the system loses entropy and the surroundings lose entropy, then the reaction will never occur spontaneously. It just won't happen because you're always going to have a negative entropy change of the universe. Okay. Now, if the system is positive and the surroundings are negative, is the reaction feasible? Well, at low temperatures, this is going to be a big number. That is very negative. And that is going to outweigh the positive entropy change of the system. So it will be negative at low temperatures. So it is not feasible. But at high temperatures, that's going to be a small number. That means that the system entropy will win out, and at high temperatures, the entropy change of the universe will be positive at high temperatures. So it is feasible. So a reaction like this does not occur at low temperatures, but does occur at high temperatures. And an example of that is, of course, calcium carbonate decomposing to calcium oxide plus releasing carbon dioxide gas, where you've got an increase in entropy of the system, but it's endothermic. At the other extreme, if we've got an equation where, or a reaction where the entropy change of the system is negative, but it releases heat because it's exothermic, for example, magnesium and oxygen forming magnesium oxide, then at low temperatures, this is a big number. This is going to win out. So it's a positive number at low temperatures, delta S universe. And therefore it is feasible at low temperatures. However, at high temperatures, this is going to be a small number, not very positive. And so the entropy change of the system wins out, and that is negative, the entropy change of the universe at high temperatures. So it's not feasible at high temperatures. So you can ignite magnesium at low temperatures, but funnily enough, it won't ignite at high temperatures. Slightly strange, but true. So summing this up, positive, positive, always feasible. Negative, negative, never feasible. Positive and negative will only occur at high temperatures, while negative and positive will only occur at low temperatures. I strongly suggest you don't try and learn this table because you'll get it wrong. You've got to just be able to reason this through. And it is complicated, I appreciate that. But it's one of those things that's asked all the time. So it is worth putting energy and effort into learning this. So let's have a look at some questions. Ammonium chloride dissolves in water spontaneously in an endothermic reaction. Identify the best explanation from this. So, ammonium chloride, we know that the entropy change of the system is going to be positive, which is good for a reaction to occur, but it's endothermic. So the entropy change of the surroundings is going to be negative, which is bad for a spontaneous process. So let's have a look. Endothermic processes are energetically favourable. No. That's bad in terms of spontaneousness. The bonds in solid ammonium chloride are very weak. Well, I don't think we can say that instantly. The entropy change of the system drives the process. Yes, it does, because the system gains entropy. The entropy change of the surroundings drives the process. No, the surroundings lose entropy. So the answer here is C. The system entropy change is driving the fact that this is a spontaneous process. Identify the combination of delta H and delta S which results in a reaction being spontaneous at low temperatures but non-spontaneous at high temperatures. Okay, well, let's think about the surroundings. At low temperatures, this is a big number, and at high temperatures, this is a small number. That's the first thing we need to do. Remind ourselves that at low temperatures, the entropy change of the surroundings is much bigger than the entropy change of the surroundings at high temperatures. If it's spontaneous at low temperatures, when this is a big number, that means that must be positive. A nice big positive number driving the reaction forwards. Therefore, why would it become spontaneous at non-spontaneous at high temperatures? Well, that means clearly that delta S system must be negative. So at low temperatures, this wins out and the reaction occurs. At high temperatures, the system wins out and the reaction is non-spontaneous. The final thing, if delta S surroundings is positive, that means it is a exothermic reaction, delta H is minus. So the combination of entropy and enthalpy change that results in this is delta S minus, delta H minus. Again, I strongly suggest you don't just learn the tables and that you try and work out how to reason these through. Identify the combination of delta H and delta S which leads to a reaction that is not spontaneous at low temperatures but becomes spontaneous at high temperatures. Again, delta S surroundings. That is a big number at low temperatures but a small number at high temperatures. It is spontaneous, it's not spontaneous at low temperatures. And this is a big number, so that suggests that is negative. The reason it must switch is because delta S system must be positive. So at low temperatures the negative wins out and it's not spontaneous. At high temperatures the positive wins out and it is spontaneous. Finally, if the entropy change of the surroundings is negative, that means the reaction is endothermic. So D, both delta H and delta S must be positive for that behaviour. The delta H and delta S values for the combustion of hydrogen are both negative, which is the correct description of the reaction. Okay, So delta S system is negative, but delta S surroundings must be positive because it's exothermic, delta H minus. And this is a small number, sorry, a large number at low temperatures, but it is at high temperatures, it is a small number. At low temperatures, therefore, that positive will outweigh the negative. The whole thing will be positive, and it will be spontaneous at low temperatures. But at high temperatures, the positive is a small number. It's outweighed by the negative, so it is not spontaneous at high temperatures. So the correct answer is B. If they're both negative, it'll be spontaneous at low temperatures, not spontaneous at high temperatures. Decomposition of limestone can be represented by this equation: calcium carbonate and calcium oxide calcium carbonate going to calcium oxide and carbon dioxide. Clearly, the enthalpy change for the reaction is going to be, it's a thermal decomposition. So the enthalpy change, delta H, will be negative, positive, meaning that delta S surroundings will be negative. The entropy change of the reaction, we're forming a gas, so delta S is going to be positive. So delta at the system is positive. At low temperatures, this will win out, so it's not spontaneous. But as we get higher, the surroundings become smaller and smaller and smaller until eventually the entropy change of the system wins out, and that becomes spontaneous at high temperatures. Finally, the enthalpy and entropy changes for this reaction. It's a hypothetical reaction. A plus B goes to C and D. There's the entropy change. There's the enthalpy change. Okay, so they're both positive numbers. So delta S system is positive. Delta S surroundings is going to be a negative number because it's an endothermic reaction. So there's going to be a flip because these are opposite signs, so we know it's not the first two because there's going to be a flip between spontaneous and non-spontaneous. At low temperatures, this is a big number, it's going to win, so it's going to be not spontaneous. So at low temperatures, it's not spontaneous. However, at high temperatures, this is a small number. The positive will win out for the system. So at high temperatures, it is spontaneous. So therefore, the reaction will be spontaneous at all temperatures above 1000 Kelvin. Right. You've now got about 30 to 40 minutes of work to do. It's on Google Classroom and it is calculating delta S system, delta S surroundings and delta S universe. It's a self-marking Google form, and because of that means I've had to be very precise with the answers that I'm expecting. So you must give them in the appropriate units, to the right degree of precision, careful with your rounding. For example, plus 123 joules per Kelvin per mole, minus 456 joules per Kelvin per mole, okay? And hopefully you will realise that you do get a lot of this. See you next week.